To size a generator, transformer, and transfer switch, firstly, calculate the minimum load that the generator must supply. With the 40 amp load on a 120 volt panel, the calculation is 40 amps multiplied by 120 volts, which equals 4,800 watts, or 4.8 kilowatts. Secondly, apply a diversity factor. This factor accounts for the fact that not all equipment will be running at full capacity simultaneously. A typical diversity factor for residential applications is 0.7. Multiply the minimum load by the diversity factor, which is 4.8 kilowatts multiplied by 0.7. This equals 3.36 kilowatts. Therefore, the minimum generator size should be 3.36 kilowatts. However, you should choose a generator larger than this minimum to provide ample capacity for any additional loads or future expansion. Given the existing 17.5 kilowatt generator, it is suitable for this application. To size the transformer, you need to determine the phase of the generator. In this instance, it's a three-phase generator. You must also determine the load phase, which is a one-phase load. Calculate the transformer ratio by dividing the generator voltage by the load voltage. In this case, 208 volts divided by 120 volts equals approximately 1.73. Calculate the transformer kilovolt ampere, or kV amps, rating by multiplying the generator kilowatt rating by the transformer ratio. This is 17.5 kilowatts multiplied by 1.73, which equals approximately 30.425 kV amps. Choose a transformer with a kV amps rating that is closest to, or slightly above, the calculated value. A 30 kV amps transformer would be suitable in this situation. To size the transfer switch, determine the rated amperage of the panel. In this case, the panel is rated for 100 amps. Choose a transfer switch with an amperage rating that is equal to or greater than the panel amperage. Therefore, a 100 amp transfer switch is suitable. It is important to note that these calculations provide a basic estimate of the required equipment sizes. It is always recommended to consult with a qualified electrician for more precise sizing and to ensure compliance with all local electrical codes and safety regulations. Additionally, ensure that the generator is capable of supplying additional load above the minimum calculated load to account for potential future expansion or equipment upgrades. It is critical that the transfer switch is properly interlocked with the utility service to prevent backfeed into the electrical grid, which could pose a significant safety hazard. A backfeed situation can endanger utility workers and damage electrical equipment. For more accurate generator sizing, consider these additional factors. Firstly, motor starting requirements. Motors require significantly more power to start than they do to run continuously. This is often referred to as inrush current or locked rotor amps. The generator must be able to handle these inrush currents without significant voltage drop. Consult the motor's nameplate for locked rotor amps information and use appropriate multipliers to determine the generator's surge capacity. Secondly, harmonic distortion. Nonlinear loads such as electronic devices and some types of lighting can introduce harmonic distortion into the electrical system. Harmonics can overheat the generator and other equipment. If significant nonlinear loads are present, consider using a generator with a total harmonic distortion rating suitable for the application. Thirdly, altitude and temperature. Generator power output decreases with increasing altitude and temperature. Consult the generator specification sheet for dating factors based on the installation location's altitude and temperature. Fourthly, fuel type and availability. Consider the available fuel types, such as natural gas, propane, or diesel, and their availability in the area. Each fuel type has different energy content and storage requirements. The generator's fuel consumption rate should also be factored into the overall cost of operation. Fifthly, automatic versus manual transfer switch. An automatic transfer switch will automatically switch the load from the utility to the generator when a power outage occurs and back to the utility when power is restored. A manual transfer switch requires manual operation. Consider the criticality of the load and the desired level of automation when choosing between the two. For a more precise transformer sizing, consider these additional factors. Firstly, transformer type. There are various types of transformers, such as dry type and liquid-filled. Dry-type transformers are typically used indoors, while liquid-filled transformers are used outdoors or in specialized applications. Choose the appropriate transformer type based on the installation environment and application requirements. Secondly, impedance. Transformer impedance affects the voltage regulation and short-circuit current levels. A lower impedance transformer will provide better voltage regulation but will also result in higher short-circuit currents. Select a transformer with an impedance that is suitable for the application and coordinate the short-circuit current ratings with the downstream protective devices. Thirdly, insulation class. The transformer's insulation class determines its ability to withstand high temperatures. Choose a transformer with an insulation class that is appropriate for the operating environment. Fourthly, K-factor. The K-factor indicates the transformer's ability to handle harmonic loads. If the transformer will be supplying significant nonlinear loads, choose a transformer with an appropriate K-factor rating. Fifthly, efficiency. Transformer efficiency affects the operating cost. Choose a transformer with a high efficiency rating to minimize energy losses. For a more accurate transfer switch sizing, consider these additional factors. Firstly, neutral switching. Some transfer switches switch the neutral conductor, while others do not. If the load is sensitive to neutral voltage fluctuations, choose a transfer switch that switches the neutral. Secondly, bypass isolation. A bypass isolation transfer switch allows the transfer switch to be bypassed for maintenance or repair without interrupting power to the load. This feature is useful for critical applications where downtime must be minimized. Thirdly, surge protection. Consider using a transfer switch with built-in surge protection to protect the load from voltage surges. Fourthly, communication capabilities. Some transfer switches have communication capabilities that allow them to be monitored and controlled remotely. This feature is useful for applications where remote monitoring and control are desired. Fifthly, agency listings. Ensure that the transfer switch is listed by a recognized testing laboratory, such as Underwriters Laboratories, or ALL, to ensure that it meets safety standards. Before beginning any electrical work, be sure to de-energize the circuits. Wear appropriate personal protective equipment, or PPE, such as safety glasses and gloves. Always consult with a qualified electrician to ensure that the installation complies with all applicable codes and regulations. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations. Refer to the NEC for specific requirements related to generator, transformer, and transfer switch installations. Article 700.12 of the NEC covers emergency systems and their power sources. Article 450 covers transformers. Article 701 covers legally required standby systems. Article 702 covers optional standby systems. When sizing conductors, refer to NEC Table 310.16 for allowable ampacities of insulated conductors rated up to 600 volts. When sizing overcurrent protection, refer to NEC Article 240. Always follow manufacturer's instructions for installation and maintenance of electrical equipment. Ensure proper grounding and bonding of all electrical equipment to minimize the risk of electric shock. Use appropriately sized conductors and conduit for all electrical connections. Inspect all electrical equipment regularly for signs of damage or wear. Perform routine maintenance on generators, transformers, and transfer switches to ensure reliable operation. Keep accurate records of all electrical work performed, including equipment specifications, wiring diagrams, and test results. This information will be helpful for future troubleshooting and maintenance.